Today I'm going to show you how to draw Lewis dot diagrams and Bohr models. Before we do that though, we have to review a little bit about what we know about the atoms and the protons, neutrons, and electrons, and then we're going to add in one extra piece of information. So you should know at this point that when you look at a symbol, so here's my symbol right here, the bottom left-hand number is the atomic number. It identifies the element. It is also the number of protons. Then this mass number represents p's and n's added together. So if I subtract these two, I'm going to get the number of neutrons. And then everything in this box is for this symbol, just in case you didn't know. And then for electrons, we do P minus E equals C. And so since there is no charge written in, we assume the charge is 0. So 32 minus X equals 0. You get 32 electrons. So that should be old and easy. Now, the next thing we're going to look at is where those 32 electrons are, and that's where the configurations come in. So for an element with 32 electrons, if you look on the periodic table, GE's right down here. Don't worry about these charges in the top right-hand corner. Again, we ignore them until I tell you otherwise. This number down here, the 2, 8, 18, and 4, is called the electron configuration. It's also right here. It tells you what it is on the symbol in the middle. What it really represents is the number of electrons that's in each orbital of the atom. So for GE, it's 2, 8, 18, and 4. And what that means is that there is 2 electrons in the first orbital, 8 in the second, 18 in the third, and 4 in the last. So they do fill in a specific order. You do not have to memorize the order as long as you use the periodic table. I'll get more into that in a minute, but basically it is the last number. The configuration tells you how many electrons are in each orbital. Now, the last number is special. It is called the valence electron number. The reason it is special is because if you think of an atom like an onion, right? Or here's our atom, right? There's my little nucleus. The orbitals are layered. So the outer orbital is called the valence orbital, and the electrons in it are called the valence electrons. Since they're the outer orbital, when an atom comes in contact with other atoms, it's the outer ones that actually do the contacting, and therefore they're the ones that form chemical bonds, and they are the most important, which is why they get a special name. So valence electrons are the electrons in the outermost orbital. They're used in bonding. They're the most important. And they're used in bonding. And that's pretty much it. Now, there is a maximum number of electrons that can fit in each orbital. There's actually a formula for it too. If n is the number of orbitals, the formula is 2n squared. You don't have to worry about that. You just need to know the numbers. So in the first orbital, there's a max of 2 electrons. In the second, there's 8 electrons. In the third, there is 18. In the fourth, there's 32. And in the fifth, there's 50. Now, you only really need to know 2, 8, 18. You're rarely ever going to use atoms that have a full fourth orbital. And just remember, they don't fill in a linear order, meaning in the beginning, orbital 1 will fill, and then orbital 2. But after orbital 2 fills, the order isn't linear. It's not like orbital 3 completely fills, and then 4, and then 5. There's something more complicated going on, which is we're not going to learn. But as long as you follow the filling order on the periodic table, you're never going to have to know it. All right? So that is what we need to know in order to draw Lewis and Bohr models. Also, the orbitals can be called principal energy levels. That's another name for an orbital. It can be abbreviated PEL, but the key there is that orbitals are also known as energy levels. That will come into play in our next lesson when we talk about electron transitions and things like that. So how do we do Lewis dot diagrams? Well, if you look at the symbols in the periodic table, so I'm going to do these symbols, L, I, B, E, B, C, N, O, N, E, and F, right? Now, looking at the periodic table, the configurations are right on the bottom. 2-1, 2-2, 2-3, 2-4, 2-5, 2-6, 2-7, 2-8. They go left to right across a period. So if we look at them, the reason I chose these is because their valence electron numbers increase by 1 every time. So if you watch how I write the orbitals in, it's very easy. If the atom has 1 valence electron, the way I draw a Lewis dot diagram is I draw the symbol, and then I put 1 dot to represent the 1 valence electron. Now, why would we use a Lewis dot diagram? Simple. A lot of times, the only thing we really care about in an atom is how many valence electrons they have, because the valence electrons are the ones that do bonding, and we don't really care about anything else. So a Lewis dot diagram is just a way of very quickly and easily representing the symbol, the element, and how many valence electrons it has. We're going to use these to draw atoms or to draw chemical bonds. So there's one. If there's 2 valence electrons, first dot goes on the top, second dot on the side. Think of the symbol as being boxed in, and this is actually your order. The first box would go here, your first dot, second dot, third dot, fourth dot, and then if there is a fifth, it goes next to the first. The 6th would go next to the second, the 7th would go next to the third, the 8th would go next to the 4th. So let's take a look. 3 dots would go like this, 1, 2, 3. 4 dots, 1, 2, 3, 4. 5 dots, 1, 2, 3, 4, 5. 6 dots, 1, 2, 3, 4, 5, 6. You should see how this is working. It should be pretty easy. 1, 2, 3, 4, 5, 6, 7, and then 8 would just be going around twice. Now, I will bring this up later on when we start doing bonding, but it's actually really simple. It's really easy to figure out. Once you know how to do Lewis dot diagrams, figuring out how many bonds an atom is going to make is very, very easy. Just listen, and if you remember this, it'll make your life very easy for the rest of the year. The single valence electrons will form bonds. The paired up ones won't. So if we look at it, lithium's only going to make 1 bond. Be will make 2. Boron will make 3. Carbon will make 4. Nitrogen only has 3 singles. The pairs don't count anymore. So nitrogen goes back down to 3. Oxygen goes back down to 2. Fluorine goes back to 1. And neon doesn't make any because it has 4 pairs. And so if you know that, we'll learn that later on again, and obviously I'll review it, but that's actually a very easy way of figuring out how many bonds the atoms want to make most of the time. Okay, and I forgot to write this in. You don't need to, but 2, 8, 18, 4. So let's flip the page, and I will show you how to draw Bohr models. They're basically just a different way of representing the information that's right in this box right here. That's all a Bohr model is doing, is it's representing that in a atomic model instead of on a piece of paper. So before we do that, we do have to worry about a couple things. All right, so if I looked at the element chlorine, chlorine on the periodic table is atomic number 17. So it has 17p, and when it has no charge of 0, it would have 17e, and if we look its mass up on the periodic table and subtract, round it and subtract, we get 18n. So now I'm going to compare, and there's a very specific reason I'm doing this. I want to compare the Bohr model, or the Lewis model for this chlorine, which has a charge of 0, and chlorine here, which has a charge of -1. All right, so let's fill in all the information first, and then I'll show you why. So this chlorine is also 17 protons. It has to be, it's chlorine. It's also 18 neutrons because the mass hasn't changed. The difference is, since it has a -1 charge, it's going to have 18 electrons, which you should be able to do. This should not be hard. The configurations are going to be different, and this is where the configuration comes in. I'm going to show you how to do it now, and we're going to use it for the Bohr models. Now watch. If we go to the periodic table and we look at chlorine, chlorine's configuration is 287. So I'm going to write that down. If you add 287 up, it adds up to 17 electrons, which is good because chlorine has 17 electrons. That has to match. Now, chlorine -1 has 18 electrons, so I cannot say that it has a configuration of 287 because that would not add up to 18. So here's how I do it. If I need a configuration that adds up to 18, instead of going to chlorine, which is element 17, go to element 18, which is argon. Its configuration is 288. And if I add that up, it adds up to 18. Now, I'm not saying that this chlorine is now argon. All I'm doing is I'm borrowing the configuration for 18 electrons because the electrons don't fill in the exact order that you would expect them to. Obviously, this one did in this one particular instance, but if you look at these elements over here, they don't fill in an order that you would expect. And what it comes down to is you don't know enough yet to explain why they fill in that order. So we are going to rely on the periodic table, which has that order pre-done for you so that you don't have to memorize the filling rules. If you really want to know the filling rules, you can contact me or see me after school and I'll go over it, and you probably won't want to have to memorize it, but you're more than welcome to. So watch how the Lewis dot diagrams work. Remember, for Lewis dot, we care about valence electrons only. So in this case, the last number. So like you would expect, for this chlorine, you would get 7 dots. And for this chlorine, now it has 8 valence electrons. So it gets 8 dots. Not a big deal. This is the reason I took the time to show this to you, because in this problem, it's a little different. So let's do it. Calcium is atomic number 20. So they're both going to have 20 protons. Calcium, the weight off the periodic table, because I have no way of knowing the weight, so I take it and round it, is 40. 40 minus 20, 20 neutrons. This calcium has a charge of 0, so it's going to have 20 electrons. This calcium has a charge of +2, so it's going to have 18 electrons. Now, when I look up the configuration for 20 and 18 electrons, it's pretty simple. For 20 electrons, it's 2, 8, 8, 2, because that adds up to 20. For 18 electrons, it's 2, 8, 8, because that adds up to 18. Hopefully this is good so far. Now, when I do my valence electrons, take a look. The first one, the valence electron number is 2, because it's the last number. 1, 2 dots. Common mistake, the reason I didn't draw these zeros in is because don't confuse them. Don't confuse the 0 for the charge, that's why we don't write it in, with a Lewis dot diagram dot. So it's not an electron, it's the charge. If you want to leave them off, fine. If you want to maybe use a different color or whatever, it doesn't make a difference to me. As long as you're aware that the zeros don't have to be written, that's part of the reason they don't have to. It's one of the reasons they don't have to be written. All right, now let's go to this one. This is the one that everyone gets wrong most of the time. And to be perfectly honest, the people who get it wrong, I kind of agree with them more than the people who came up with this concept. But let's do it. How many dots do you think this calcium is going to get? If you're saying 8 right now, then you also fell for the trick and it's wrong. Here's the issue. Calcium normally, its valence orbital is the 4th orbital. This would be orbital 1, this is orbital 2, this is orbital 3, this is orbital 4. How many electrons are in the 4th orbital? Which isn't even written down anymore. That's why I highlighted a blank spot. It would be 0. So, since it's technically a 0, we don't write it, but also that means 0 dots. Now, the reason chlorine worked out easy was because I had the 3rd orbital here, and I still have the 3rd orbital, so nothing really changed. But with calcium, it had 2 in the 4th, now it has 0 in the 4th. And so, yes, some people would say, well, then wouldn't that make the 3rd the new valence? And I tend to agree with you, but that's not what the greater scientific community says, so that's what we have to deal with. All right? So just be aware of that trick. The reason I showed it to you here is it almost exclusively happens with atoms that turn into cations or positive ions. When you have negative ions, you're gaining electrons. You almost never do that. It's almost always a positive ion where it's going to happen to. All right, so let's do the rest. These are going to be easier and more standard. So the first thing you do is you look up the atomic numbers. I am going to put them in here. So for fluorine, its atomic number is 9, for vanadium, 23, and for calcium, it's 20. So 9, 23, and 20. In terms of mass, if I look up the mass on the periodic table, which is 19, subtract, I get 10 neutrons. If I look up the mass on the periodic table, I don't know what it is, but I know when I subtract, I get 28 because I have this pre-written down off to the side of the camera. And this one is 40. Let me see, just to keep it the same. Vanadium is 51. And this one's 20. All right. Now, electrons, they should be pretty easy. I get 10 electrons, 20 electrons, because remember, positive 3 and negative 1. And this one, since there's nothing written, I assume it's 0, 20 electrons. So for the configurations, they're going to be 2, 8, and then these two have the same configuration. That does not mean they are the same element. That does not mean they have similar chemical properties. That just means that right now, under these charges, they happen to have the same valence number of electrons, and therefore they would have the same configuration. In real life, that's not actually true. Other things are happening where their configurations will technically be different, but we're never going to learn that. So good enough for now, right? We're going to keep it super, super simple. Now, how do you do a Bohr model? It's real simple. You take this information, which we just figured out, and you display it as an atom. So I draw a circle. The circle represents my nucleus. In the nucleus, you should know this at this point, there are protons and neutrons. So I write 9 and 10 for fluorine, because it has 9 protons and 10 neutrons. And since it has 2 orbitals, I would draw 2 quarter circles. Now, in real life, you would draw entire circles around the atom, but that takes up too much space, so we're totally fine drawing quarter circles. And you would just write 2, 8, done. That's a Bohr model. So it basically just takes these 4 pieces of information and puts them into the atom. And not even the total number of electrons, because you need that to get the configuration. So it's really just 3 pieces of information. So for this one, vanadium, it's going to be, draw my nucleus. There's my protons. There's my neutrons. And since I have 1, 2, 3, 4 orbitals, 4 quarter circles, or whatever you call them. 2, 8, 8, 2. Yes, you have to write the E's, the P's, and the N's. Otherwise, I won't know what they represent. And the last one. 20p, 20n, (2882). And then we're going to do, just so we know that we're doing this right, we are going to do the Lewis models for those Bohr models. So it's pretty simple. For a Lewis model, remember, the symbol and the charge. I don't need to know the mass. I don't need to know the atomic number. If you write them in, it will be marked wrong. You don't need any of that information, because Lewis is really reserved just for bonding. And the only thing we care about with bonding is the valence electron number most of the time. And so therefore, Lewis models don't have any of that extra information. They're designed to be fast, quick, and easy to write and easy to use. So for fluorine, since it has 8 valence electrons, it gets 8 dots. 1, 2. Now, beware. And part of the reason I showed it to you up here, as the charge changes, the number of valence electrons will change. And so it's important that you write fluorine with the -1. If you left the 1 off but left the negative sign on, that's fine because it happens to be a 1. But in general, you should just write the whole number and get used to it. But if I didn't include this -1, the assumption would be that the fluorine would have a charge of 0, because that's the assumption you make if it's not written in. And therefore, it wouldn't have 8 valence electrons with a charge of 0. It would only have 7, and then it would be marked wrong. So do be aware of that. This one, vanadium +3, it's got 2 valence electrons, so it gets 2 dots. And calcium, 0, you don't have to write the 0 in. 2 valence electrons, so 2 dots. And that is how to do Lewis and Bohr models.